Greetings. After solving two problems on gas turbines and steam turbines and the steam cycle, now we move to the cycle for the reciprocating engine. And this usually starts with Otto cycle, which is good for gasoline engines. Then it's the diesel cycle, which is for diesel engines. And finally, there's a cycle which is called dual cycle, which is basically a combination of both and would better represent what happens in a real engine. So the problem I solve for you now is on dual cycles, and well, once you learn how to calculate a dual cycle, then it would be very easy to just remove the diesel part and you would have an Otto cycle, or you could remove the uh, Otto cycle from it. I mean, the constant volume portion of it, and then you would have a diesel cycle. Now, a dual cycle basically consists of the following processes. If this is the PV diagram, please note that we have moved to a PV diagram since it's a cylinder piston arrangement, and a PV diagram would just fit much better, which represent much better the processes of a cylinder piston arrangement. Now, there is a start point, which is usually here, where the air has entered the engine, and the stroke wants to start. And there is adiabatic and reversible process in the ideal dual cycle, which brings it to two, is the compression part of the cycle. Then there is the constant volume part, which is basically where in an Otto cycle, it's where heat is added, and in a real Otto cycle, in a real gasoline engine, is where the spark acts and the fuel starts to burn. Then there is a constant pressure part up to point 4 in a diesel engine. This is the part where fuel is injected, and since the pressure is high, it would start to burn immediately, but it's the burning speed depends on the injection of the fuel, and since the piston is moving back, then a constant pressure line would be a better representation of the heat addition section. Then there is a process where work is done and it comes to point 5. And finally, it is process 5.1, which is heat rejection part of it. So this is our dual cycle. You know that the um, smoke is ejected, is removed in one stroke, and then fresh air is let in another stroke. That's what the four-stroke engine does, but for the process that we have, we just ignore that in the ideal process. The real process somehow is doing the same thing. I mean, the real process in every engine is like this. I mean, it is somehow a mixture of both diesel and Otto cycles. So this is a good representation of both of them. Now, what we know about this cycle is that the start point T1 equals T1 equals 300 Kelvin, and P1 equals 100 kilopascal. So these are the ambient conditions where the intake, that's air, the incoming air, has 100 kilopascal pressure and 300 Kelvin temperature. And now we have to define the different processes for this cycle. The process 1, 2 is the stroke, basically defines the stroke, is the volume ratio, and what we could say about this and what's usually said is V1 over V2 is given, which for the present problem, we assign it to be 18.1. For an Otto cycle, this is far less, just to avoid auto ignition, but for a diesel cycle, it's about the same value, and even it could be more than that, up to 24, say, but for the time being, let it be 18.1 for our dual cycle. Process 2, 3 is basically heat addition, and it depends on the amount of fuel that is available inside the cylinder. So what we say about it here in this problem is that Q23 equals 384.36 kilojoule per kilogram. This is the added heat during the process 2-3, which depends on the amount of fuel that is available when the spark plug ignites and that fuel is burned and heat is released. But for the ideal cycle, we just assume that this is the heat that we have added to the cycle. Process 3-4 depends on the amount of fuel that we inject into the cylinder, and it basically says how far in the stroke, how far the piston should move back, and we still inject fuel. And the way just to present it is to give a ratio for V4 over V3, and that in our problem is 1.209. And you shall see that I have selected these values such that when we go to a table, we would not have to do interpolation. If I had done otherwise, then we would have to do some interpolation when we go to the tables. Well, these are our information. Of course, V5 is equals V1 because it's the end of the stroke and it's the bottom dead center for our cylinder and for our piston. Now, processes 1, 2, and 4, 5 are isentropic processes. So for 1, 2, we may write P2 over P1 equals V1 over V2 to the power gamma, and T2 over T1 equals V1 over V2 over gamma minus 1. This is the case if we assume that air is perfect gas, which is good enough, but there's another assumption to it, is that we assume that specific heats are constant. We shall see how far from truth this assumption is in this case. And therefore, we have to use, and we would use, a different method which provides us with data when specific heats are not assumed constant and are assumed variable. And that is when we use V2 over V1 equals VR2 minus VR1, and P2 over P1 equal PR2 over PR1. You see, these equations are valid for isentropic processes. So these two equations, just like the above ones, are all valid for isentropic processes. Here, PR and VR are both functions of temperature, but they are directly proportional to specific volume and pressure. So we could write that PR and VR are functions of temperature, but VR is directly proportional to volume, specific volume, and PR is proportional to pressure. These are the two properties that are listed in tables. In fact, many thermodynamic books have tables which give these values, and if you look at it here, you would see I've selected this table from the book by Senja, and similar tables for air are there in other thermodynamics books. And what you have different temperatures in the first column, and then you have enthalpies in the second column. You see that for perfect gas, enthalpy is just function of temperature. Then you have PR, which is basically directly proportional to pressure. This is a function of temperature, which is directly proportional to pressure. This is U, which is basically CV0T, what CV is changing with temperature. This is VR, which is directly proportional to specific volume, and this is standard entropy, which is also a function of temperature. So this is the table that we shall refer to, and any value of any of these columns, if we manage to calculate, then it would be very easy to just read other values on this table and from this table, and we shall do this practice in such problems quite often. So let's return to our problem and start just finding the solution. You see, a very key way to solve this problem is to find properties at different points. And it's just a good practice for all cycle problems. And I would recommend this practice for every problem that has a cycle, is that you draw a table just like this, and then you place different values. And the first thing you should do is to find different properties on this table, fill in this table, and then it would be very easy to just proceed with other solution. This is in line with our general practice that we have always followed, that find properties, then decide on the control volume, write equations, write governing equations, simplify them, and draw the diagram, which we have already done so, and then get everything together towards the final answer. And this is the practice I suggest for this problem. So what we have for the time being is that in this very problem, we know that T1 is 300 Kelvin. This is 300, and P1 is 100. This is the two values that we already know. And since it is air and it is perfect gas, what we could do is to calculate a specific volume. And the a specific volume is V1. V1 equals RT1 RT1 over P1, which is 0.287 times 300 and divided by 100. And it gives us, we want the specific volume to be 0.861 cubic meter per kilogram. That is V1, and we may write it here. V1 is 0.861. All other properties in this row may be completed from the table I just showed you. And U would be 214.07. H is 300.19. PR is 1.3860, and VR is 621.2. That's all there is to point 1. We are now completed point 1, and we could move to point 2. As for point 2, the process is isentropic. That means 1, 2 is isentropic. And we know what the volume ratio is. So what we know is that we just move to this equation. We know that V1 over V2 equals VR1 over VR2, and that means that 80.1 equals 621.2 divided by VR2, and therefore VR2 would be 34.31, and referring to the table, we get that T2 equals 900 Kelvin. If T2 is 900 Kelvin, then we could also complete different boxes in this table for just the knowledge of T2 is 900 Kelvin, and therefore we know that U would be 674.58, H is 932.93, PR is 75.29, and VR is 34.31. Now, we know that PR is a function of temperature, which is directly proportional to pressure. So we may use this value to calculate pressure at point 2. That's how we do it. P2 over P1 equals PR2 over PR1, and therefore P2 is 100 times 75.29 divided by 1.3860, and the final outcome is P2 equals 5432.2 kilopascal. This is the pressure at point 2, and we could calculate V2 from a knowledge of P2 or T2, or we could just divide VR2 by, we could just use this equation and divide V1 by 18.1 and see that V2, I just write it here to complete this section. V2 equals V1 over 18.1, and that equals 0.04757 cubic meters per kilogram. And let's just insert these values into the table. So for point 2, pressure is 5432.2 kilopascal, and the specific volume is 0.04757, and we have now a complete knowledge of point 2. Well, the next step for process 1, 2 is to simplify the governing equations, and that's very simple for these cycles since there is no mass entering or leaving the cylinder. That's how it is in the ideal cycle. So these two terms, and these two terms vanish. It's M2 minus M1 equals 0. Here, there is only the change of energy, which equals heat transfer and work, whichever is available in that process. And in this equation, there's, at least for process 1, 2, there is no heat transfer. It's an ideal process, reversible process for the ideal cycle. These two terms also vanish since there's no mass entering or leaving, so the initial and final entropies are the same. So what I would do is to write down these equations for process 1, 2, which M2 minus M1 equals 0, also, so we could just simplify all equations and write them for unit mass. U2 minus U1 equals minus W1, 2. There's no heat transfer, and the S2 minus S1 equals 0. That's all there is to it. So what we could do is we could calculate the work of the first process, and W12 would equal U2 minus U1, which we have both of them in our table, which are here. It is 674.58 minus 214.07, and the outcome is 460.51 kilojoule per kilogram. And please remember that there should be a negative sign here, which minus W is this work, but W12 is minus 460.51 kilojoules per kilogram of air. Good. So this is the work, in fact, which is done on the air inside the cylinder. You see, the practice is very similar to what I told you before. I mean, we do work on, we compress a cold volume, a cold fluid, then we give it heat, and then we expand it. And the work gained from expansion of hot air or hot medium, whatever it is larger than the work already done for compressing, and the outcome would be some positive work. That's what we will do. Now, let's move to point 3. As for point 3, what the knowledge that we have for point 3 is that is the amount of heat that we add to it just to heat it up. This is the energy released from the fuel that is burned at point 2, and it is 384.36. So as it is, when we have Q, we have to basically write our equations for process 2, 3, and then see how heat release would be related to properties. For point 3, M3 minus M2 equals 0, which is the constant mass. U3 minus U2 equals, well, of course, there's no mass that enters or leaves, that's no problem, but there is no work because there's no movement between 2 and 3. Therefore, there is only heat, which is Q2, 3. And then, of course, the second law is that S3 minus S2 equals Q2, 3, and divided by temperature. We don't usually need that equation. We don't use it here, but this one helps us a lot, since U3 equals U2 plus Q2, 3, and the outcome is 1058.94 kilojoule per kilogram. And once we know this value, this is one of the values in that table, and so it would give us a lot more values in the table. So let's just fill in U3 in our table, which is 1054.94, and therefore we would have first temperature for point 3, which is 1340. That's the temperature. We don't have yet the specific volume, but we have H, which is 1443.60, PR and VR. Oh, of course, we could read them, but they are irrelevant because point 3 neighbors know isentropic process. So we couldn't, in fact, use PR and VR in that process. They would be of no use to us. Now, the other knowledge that we have for point 3 is that the specific volume is equal to point 2. So its specific volume is also 0.04757. The only unknown left for us is pressure, and the pressure at point 3 would be just it is perfect gas. So we could write it as P3 equals RT3 over V3, and that is 0.287 times 1340 divided by 0.04757, and the outcome is 84.51 kilopascal. That's the pressure at point 3, and we may also complete our table here. It is 84.51. We have now calculated all values for points 1, 2, and 3. We have all required knowledge for heat transfer or work for processes 1, 2, and 2, 3. And the next step that I shall do in my next video is to calculate values for points for processes 3, 4, and 4, 5. Okay, cheers.